Okay, so today we have Matthew Yu, which is a postdoc at the Mathematical Institute of the University of Oxford. Before that, he was PhD at the University of Waterloo, working at the Perimeter Institute for Theoretical Physics. He focused on studying mathematical aspects of quantum field and string theory, bringing in idea of homology theory and higher fusion category. Matthew, please. You can start.
Okay. Well, yeah, thank you for the introduction and thank you for giving me the opportunity to speak here. Yeah, I will be telling you about some recent works on the classification of fusion 2 categories. So let's get started. I want to start by giving the definition of a fusion 2 category. So just so everyone's on the same page, a fusion 2 category is a finite semi-simple monoidal 2 category with duals and simple monoidal unit. So just to get the definition out of the way for everyone, I will give sort of more examples of what this thing is, but I want to give the definition so that we're all on the same page. And then let me begin by saying sort of some backgrounds and motivations for this project. And let me start with some of the physical motivations. So in particular, there's been a lot of interest these days on kind of symmetry operators in higher dimensional QFTs. So, for example, in 1+1 dimensions, the fusion 1 categories have, made lots of contributions to these types of things, and we've seen examples of this. For example, the Ising CFT and other quantum systems. And so now the interest is really going to higher dimensions and focusing on 2+1D. And to go to even higher dimensions, you can imagine that you need to generalize to maybe like a 3 category or something else. The fact that this category is semi-simple is going to be quite important in our discussion today. And so, these are only capturing kind of the semi-simple symmetries that one really cares about from a physical point of view. But it turns out that there's lots of information that's a quantum field theorist would already care about that the semi-simple category can already tell you. And so to break this down, right? So if we take a fusion 2 category and we call it C, then the objects of C are the codimensional 1 operators in 2+1. So these are surface operators. And then the morphisms in this one are the codimension 2, and then you have the point operator. So these give you basically the 0 form symmetries, the 1 form symmetry, and the 2 form symmetries in 2+1D. So there's another perspective that people have taken to symmetries in quantum field theories, and this is via the SymTFT. And so the idea is that kind of you could capture aspects of the symmetry on the boundary by looking at a topological field theory built up of something related to this category. It's really built out of kind of the center of this category using this Reshetikhin-Turaev construction on the center of this category. And then this creates for you a quantum field theory from which you can study certain gap phases of the boundary theory by looking at boundary conditions of this topological field theory we mentioned higher. So this perspective has been quite powerful lately, and we'll also see kind of how this SymTFT plays a role in the classification as well. And then going beyond kind of regular or just general 2+1D QFTs, fusion 2 categories have also been quite important for the study of topological field theories on 4D and 5D. And so the reason why they're important is because kind of there's been some classifications that you can do kind of going along the work of Liang Wen and Theo Johnson-Fried, that kind of they've axiomized what it means to be a topological order at higher dimensions. And then you see that kind of in this dimension, fusion 2 categories, maybe with some extra structure, turns out to be the right type of mathematical object to describe these PQFTs. So now, if you're a mathematician, our classification also has some interesting results. And I want to start by first, saying kind of the biggest punchline that we have in this whole program is that fusion one categories, right? Like let's say you want to classify fusion one categories given kind of some knowledge of like zero categorical data. So for example, if you had the knowledge of like groups and you had the knowledge of like algebras and how like how these algebras can act on the groups, or and how these groups can act on the algebra, I should say. Then this zero categorical data isn't actually enough for you to recover all the fusion one categories. In particular, there's sort of many exotic examples of fusion one categories that just don't arise groups. And so even if you had sort of a complete classification of kind of group theory, then you still wouldn't be able to recover all the fusion one categories. But now, towards the second point is sort of, if you wanted to classify fusion two categories up to monoidal equivalence, what you can do is you can sort of imagine that you had a classification of braided fusion one categories, right? It turns out that sort of if you black box a classification of braided fusion one categories, so I knew everything about braided fusion one categories and sort of the Picard groups, then the classification of braided fusion two categories, like there's no other kind of wildness that goes on. Like all the wildness is just happening in kind of fusion one category land. And if you had that, then actually fusion two categories just boils down to some extra data, which happens to be some knowledge about finite groups and some cohomology. So that's a nice kind of fact that our classification gives you. But in particular, there's some more higher analogs of certain properties of fusion one categories that you would try to generalize to higher categories. So for example, there's this notion of Ockniana rigidity for finite or for semi-simple one categories, and also this notion of rank finiteness. And by studying this classification, you could just kind of probe the rank finiteness and the Ockniana rigidity of fusion two categories. And so kind of another thing that you could think about is sort of how to generalize these techniques, and does it give you a hint of sort of the structure of higher semi-simple categories? And I may be able to say a little bit more about that, but this is just one of the first steps to sort of understanding symmetries in higher dimensions and the complications that can arise. So let me begin with some examples of fusion two categories. So I assume that people haven't worked with fusion two categories before. I've given you a definition, but I want to unpack this definition a little bit more in some concrete examples and some things that you can actually get your hands on and work with, especially if you're a physicist and you want to compute things. Let me first introduce two types of fusion two categories. I will introduce fermionic / bosonic fusion two categories, and to see if a fusion two category is fermionic or bosonic, you look at kind of the loops of this fusion two categories, and you take Z2 of this, which is the Muger center. So you take Muger centers of this one. This is so it's a Muger center of a braided fusion one category, and you see if it's super Tanakian or just Tanakian. So if it's super Tanakian, then it's going to be fermionic. If it's just Tanakian, it's just bosonic. And our classification really kind of stratifies into these two types of cases. These cover all the fusion two categories that you would want. And so let me start off with a simple example. So let me define a simple a fusion two category with only a single component, namely the component that's kind of built around the identity object. We call it a connected fusion two category. These were sort of the first examples of fusion two category that was originally in the paper of Douglas and Reuter. And so the first example that you might that you come across is the category 2 rep G, the kind of two representations of a group G. In particular, here I have in mind like a zero group, but you can also in general feed in like a 2 group. And so this fusion 2 category is built out of a fusion 1 category, where you kind of take something called the suspension of this. And another way that you could write the suspension, this is sort of a notation, but sort of people have also denoted this as kind of you take mod with respect to the thing inside. And so what this mod does is sort of it says you take your category and then you do a de-looping of the category, kind of like how you can group. And then there's also a notion of kind of Karubi completing to getting all the other objects, right? And so this procedure of delooping plus Karubi completion helps you build this new category. And it's sort of a non-trivial fact that doing this gives you something that's semi-simple, but nevertheless, it becomes a semi-simple two category.
Can I ask you a question? What do you mean by component with only a single component?
So yeah, so I'll get to more specifics of this. In particular, I'll unpack it in a specific example. That's just going to come up. But the idea is that sort of, in a semi-simple one category, you sort of just have objects labeled around, right? But kind of in a two category, what you could have is you could really kind of have connected components, and then maybe objects and the components are kind of related by some morphisms.
I see.
And so kind of, a Fusion 2 category in general will have many disconnected components. And so a connected Fusion 2 category is just, you imagine you only have a single component, and then there's the identity guy sitting in. This is kind of small, I apologize.
I see. Thank you.
And so essentially the idea is that kind of you took a Fusion 1 category and you suspended it up. And when you suspended this Fusion 1 category, you just got a single. Okay. So yeah, I want to sort of unpack this in a particular example so you can actually compute with these things. So the objects of this are going to be labeled by, well, first you take a subgroup of G called H, and then you take an isomorphism class of GH sets, and then you sort of take another two cocycle in H with C star coefficients. And so these label basically like all the objects. The objects are really just labeled by kind of subgroups you can think of G. And then you would like to compute some fusion rules of these things, just like you would do in Fusion 1 categories. And if you would like more kind of details about how fusion rules are computed in general, because I'm going to just do a simple example, I refer you to this paper of Greeno. So let me do just the case where G is equal to Z2. So the subgroups are, of course, just the identity and the group itself. And the H2 cohomology of both things are trivial. So I'll just denote the two objects by kind of one object is the identity object and another object is Z2. And then according to the paper of Greeno, the fusion rules of these two things gives you basically, if you take this one and you fuse it with this one, you get two copies of the object itself. But then you also have to account for the one morphisms. And so you can look at you want to look at kind of the one morphisms with respect to this object, the one morphisms with respect to this object, and maybe there's some one morphisms that go between the two things. And indeed, you'll find that you have two simple one endomorphisms of the identity object, and they just correspond to the two reps of Z2. So this is just like this morphism is just saying that I have a morphism from this object to itself. And that's given by a one category, and that one category is literally just regular rep of C2. And then you also have two endos of this guy. These are formed by the category of vec C2, basically by the similar logic. And you also have morphisms between the two objects, but these morphisms are like almost trivial. They're given by kind of the one category of just all vector spaces. And so when you unpack what this category looks like, well, this category looks like I have an object here, I have an object here, here's the one morphism, and the other one morphism, and sort of there's a morphism in this way called back and a morphism back. But you see that kind of this category is completely connected. And therefore, this object xz2 is in the same component as just like the identity object. And sort of in another parlance, it's sort of saying that kind of it's really like a condensation of this object. It's saying that kind of there's maps to and from, right? Kind of if I go this way and I go back, then I map to basically this object up to some natural transformation. But nevertheless, kind of in Fusion 2 categories, the interesting things that you see is that you form these components of objects, and these objects can be related by non-trivial morphisms. So the second example is another example of a connected category, which is just I take vec of an abelian group, in particular an abelian group, and I take the suspension of it, or I take mod of this, And this gives me 2 vec, but now this group is suspended up a degree. So if you like, this A box 1 is like kind of it's like kind of a 2 group or yeah, it's kind of like a 2 group, right? Like the classifying spaces or like as an Eilenberg-MacLane space is given to you by K A comma 2. And so this in itself is also a connected fusion 2 category. And the reason why is because the group that you put in was connected, right? Because this thing is sort of the de-looping of A. So that's just a point, and then you have the maps of A going into it. So this category is also connected. Okay. And then sort of another important type of fusion 2 categories are what's known as strongly fusion. So definition is a fusion 2 category C such that when you look at the lines of C, right, de-looping it takes the lines of it. If it's vec or if it's super vector spaces, then we say it's strongly bosonically fusion or strongly fermionically fusion, depending on what this vector is. And so if you want to kind of construct these types of fusion 2 categories, and you can also classify these strongly fusion 2 categories easier. So in the bosonic case, they just look like basically 2 vec of G, where G is some finite group, and a cocycle in H4. Or in the fermionic case, they're given by a group G, and then you have a cocycle. But this cocycle is kind of well, it's a little bit more complicated. I'll unpack the fermionic case in a little bit more detail later on. But sort of the idea is the same. Is sort of you have two supervector spaces, G with a cycle in twisted super cohomology, whatever that is.
Matthew?
So okay, so yeah.
Can you repeat what is omega?
Yes.
Omega C convex.
So taking omega C is you should really think of kind of omega and sigma as being kind of adjoints to each other. So sigma is sort of like you take a thing and you kind of suspend it up, kind of like in topology, and omega is like you take the loops of it. So the idea is that if you have a fusion 2 category, the fusion 2 category, remember, has objects that are surface and like the kind of the morphisms are line operators, and taking omega just means I want to take the line operators inside this, right? So kind of the morphisms inside. See, another way to think about this is you take the endomorphisms of the identity object of this, and that's just vector spaces. So it's like saying that basically all the lines, like it's like you have a fusion 2 category, but the lines are all trivial, is the idea. So you just have information about the surfaces. And what's really nice about these categories is that, as you can see in this example, so thank you for pointing it out. As you can see in this example, you see these categories, like it really just boils down to like the group data, right? Because somehow after I've killed all the lines, then the fusion rules of the surfaces are just group-like. So this is different than in the case of this 2 rep C2, right? Because there, if I take 2 simple objects, I get a sum of objects. But here I'm saying that kind of it fuses like 2 vec G. So if I take 2 simple objects, then a simple and a simple is going to give me another simple labeled by some other element of G. So this is the effect. Okay, so one more kind of example.
I think
sorry.
Yeah, and in regards to the small omega, that super cohomology class, that K twisted, can you say something about that K?
Yeah, so good. So this is this kappa. Yeah, I didn't say the kappa yet, but I'll unpack the kappa later on. So in general, kappa is going to be an element of H2 of G with Z2 coefficients. And kind of I'll say a little bit about why this is important. And the idea is that kind of when you want to define the fermionic things, what you really want to define is sort of a Z2 extension of a bosonic. So you have a fermionic group that looks like this, and kind of this kappa is telling you the extension that's going on here. So really what you should be feeding in is kind of a fermionic group. This is sort of hidden by the fact that I put S back rather than back.
Okay.
Does that answer the question?
Yes.
You'll see this kappa more later on, but yeah, and I'll go into more detail if it's confusing.
Like the moment you wrote down where kappa is, I kind of got it. So
Yeah, sorry about that.
Thanks.
Okay. So the next example is a higher analog of the Tabari-Yamagami fusion 1 categories. And so you'll recall the special property about Tabari-Yamagami fusion 1 categories is that sort of, I'll just kind of write this on the side, is that the TY1 categories are really kind of Z2 graded extensions of vec G. And the idea is that sort of I'm going to have an object. You're going to have an object in the non-trivial component, such that when you square it, you kind of get the sum of all the G's in the trivial graded component. So that's the name of the game for fusion 1 categories. And so kind of we want to do the same thing for fusion 2 categories. So this is the simplest example of a Tabari-Yamagami fusion 2 category. So I call this thing Ty of Z2. So Z2 is basically like this G up here. And so this category is kind of interesting, right? It's sort of, you have these components, you have the identity component over here, and you can kind of ask yourself kind of, how does this object here, so this guy is in the non-trivial graded component, right? This D is this D. So you can fuse this guy together, and you see that D squared gives you X and Y, and these guys are sort of in the non-trivial, are sort of in the trivial component. I'm sorry. So D squared gives you the sum of these things. And then of course, you can fuse objects inside the trivial graded guy, and you get a fusion rule that looks like this. And then there's one more interesting thing, which is that kind of, if you take an object and you kind of fuse it with D, you should get D back. And so this is like the absorbing property of this object, right? Because you have something, the 0 graded component, the 1 graded component, you have to get a 1 graded component back. So we construct this in work with Thibaut Decopé, and so you can construct it basically out of kind of taking bimodules of vec D8 with vec C2, which is an algebra side. So that's a non-trivial example of fusion 2 category. This is probably as much as you'll need to sort of get a handle on the types of things. Okay, so I want to say a little bit about the ideas of the classification. So I'll harp on the ideas, like the overall philosophy, and then I'll kind of tell you a little bit about the physics, and then we'll get into sort of more of the specifics of like how to mathematically do such a thing. So here's the idea of the classification. There's two results about kind of looking at the fusion 2 category and looking at up to Morita equivalence. I should say that the classification does things up to monoidal equivalence, but let's just look at the Morita equivalence at the moment, so to sort of give us a hint of what direction we should be heading. So if I gave you a bosonic fusion 2 category, C, I know that up to Morita equivalence, every bosonic fusion 2 category is given to you in kind of the following, I can split it in the following way. I can say that it's 2 vec G with a pi. So this is this strongly fusion thing times an invertible thing. So the slogan is that the bosonic fusion 2 categories are Morita equivalent to something that's strongly fusion attached on some invertible fusion 2 category. What does it mean to be an invertible fusion 2 category? Well, again, it's the suspension of a fusion 1 category, but this thing is, in particular, it's a non-degenerate braided fusion 1 category. So this is the important part. Like, if B is specifically non-degenerate, then the suspension of it ends up being invertible. And I really mean invertible in sort of the Morita, kind of the +2 Morita category, right? That's what I mean by invertible. And fermionically, there's kind of another, almost a splitting, but not quite, which is that you could kind of find a Morita equivalence to something that looks like this. But this doesn't quite split. There's sort of an extension. There's sort of an extension here that doesn't quite split. And what you need to do is you sort of need to you need to actually go in and sort of pick a minimum non-degenerate, sort of a minimum non-degenerate extension to actually split this. And then there's sort of 16 different ways. MNEs that you can actually choose to do this, so it doesn't split canonical. And kind of this is what's creating the headache in the fermionic classifications, that this doesn't quite split. I should say that kind of this is B tilde, that these B tilde, in this case, in the fermionic case, it's slightly degenerate rather than non-degenerate. And what that means is that the invisible object, or the Muger center of this, is given by supervector spaces. So now, because there's no way to split this thing, right? A priori, this omega, which is the thing you kind of saw before, it's not quite a class of this yet. It becomes a class when I actually pick pick an extension, but before that, it really just lives in a torsor over this twisted homology. It's reduced, and so this symbol means reduced twisted. But these two facts are already quite important. It really unpacks a lot of the data of the fusion 2 category. So, good. So yeah. So I just wanted to say, yeah, just a slight repeat is that essentially modulo this weird extension problem, then it really just looks like kind of graded extension theory, right? It just kind of looks like a G extension theory of something that looks like one category stuff. And kind of from there, we can already, just from that knowledge, we can already unpack some of the physics, kind of looking at it from the SymTFT point of view. So I want to give a little bit of kind of physical perspective and a little bit of intuition for what's going on so far. And the idea is to really think of a fusion 2 category, right? If I give you a fusion 2 category, you should really think of this as kind of a bulk boundary system, right? It's like a fusion 2 category is sort of the knowledge of a bulk and a boundary. So let's C be a fusion 2 category. Let it be the kind of the set of symmetries in a 2+1D TFT. It doesn't really have to be a TFT, but this one should just be a regular QFT. So when I say it's a set of symmetry, it means that kind of this QFT, it's a module for this category. And let ZC represent the SymTFT. This lives in, it lives in 3+1 dimensions. And this is the topological theory in 1 dimension higher. So, right. So since C is Morita to this guy, we can use the fact that sort of if you're Morita equivalent, then you have the same centers, right? So kind of I can do manipulations on the boundary thing, but I can still maintain the same bulk, which is just saying that kind of the bulk admits like different types of boundaries, and the things on the boundaries are related by invertible bimodules. So this is the idea. The idea is that kind of I could take this guy, C, and in the bulk, I can use this Morita equivalence to say that Z of C is the same as Z of the right-hand side. Well, Z of the right-hand side, this invertible part goes away. So really, this just looks like G Digraph-Witten theory, right? It's some sort of higher Digraph-Witten theory. And the name of the game is to study kind of boundary conditions of the Digraph-Witten theory. So the first thing you can do, which I'll call kind of the minimum boundary conditions, is that you just look at the background G fields, and you can pick some Dirichlet boundary conditions for these G fields. And all the other minimum boundary conditions just arise from basically gauging a subgroup of G inside. And so in this dimension, what's interesting is that we'll recall that kind of in 2+1 dimensions, you also have the freedom or the possibility to stack onto the Dirichlet boundary condition an extra 2+1D TFT, right? So if you pick some sort of minimal boundary condition that has an H symmetry, you could also attach on an A with an H symmetry. This just means that there's a map. Basically, there's an action of H into the automorphisms of this braided fusion 1 category. So it's like saying that kind of you could decorate this this boundary condition with extra symmetries just because you live in a high dimension. And so to actually do this to kind of actually make this this whole procedure like cohesive, what you do is sort of after you stack by this extra asymmetry, you now gauge the diagonal H action. And so there's going to be some anomaly cancellation that you have to sort of actually enforce in order for this gauging to work. And sort of that's the anomaly cancellation that's going to go into the classification data. So this is the physical picture that you should have in mind when as I'm about to get into the classification. So maybe I should stop and ask for any questions at this
Okay.
Okay.
Hey,
Yeah.
So you have introduced this two Tambara Yamagami, in which you have this kind of like a Jolie defect surface, right? This D.
Yeah.
So is there like a codimension 2 version of something like a Dolby defect where this absorbing effect occurs at the level of lines instead of surfaces?
A codimension what do you mean? Sorry, maybe I'm not understanding. Like
Again,
sorry, you're saying instead of this D being a surface, you want it to be a line?
Yeah. But in 3D, basically.
Right. Well, the first thing, I don't know how to make a duality defect on lines in 3D. I only know how to get such fusion rules to work for surface operators, which are the objects in this category. Is there a specific reason why you asked about sort of the manipulation on lines?
It is well, if I like this construction of the condensation defect, right? I can imagine taking condensation completion of just the Z2 Tambara Yamagami, but it's not this, right? It's not this 2TY Z2.
Right. It's not exactly. It's not that.
So yeah, I'm just asking about the other guy, like what that does.
What is the condensation completion of so if you take kind of the modules or like the suspension of 1TY, what do you get?
Yeah.
Well, it's gonna be so the problem with doing this is that so in general, I think like the problem with suspending 1TY is that I don't think I'm gonna get a monoidal fusion 2 category because 1TY, right, isn't even braided. So it's not gonna be of this form.
I thought Tambara Yamagami on Z2 specifically is, right? Isn't that true, or am I mistaken?
TY of Z2 is icing, right? Yes. So that one, I mean, I guess like I guess that one is I guess that one is braided, but in general, like it's not, right? Like in general, it's just vec G and then you add on vec.
Right. For elementary 2 groups, you got braiding on TY. So for general BI group, it is not braided. But for elementary 2 groups, the Tambara Yamagami category has a braiding. You're saying that you can construct Tambara Yamagami on 2 groups. Look at those groups, right? One TY they're braided. That's what I'm saying. Is that true for like, let's say put in S3 or something? No, elementary 2 group. They have to be Z2 to the power. Oh, that's what you mean. Okay. Yeah, that's true. Yeah, that's right.
Right.
That's a big question. Sorry.
Sorry, the audio is a little bit hard to hear. There's sort of an echo on your side, so some of the voices get a little bit muffled when 2 people are speaking. I didn't quite hear the discussion. So, anyways, is there more questions or should I go on?
You can go.
Okay, so so to now actually get into the heart of the classification. So the idea so kind of I'll spell out the formal aspects of the classification and sort of how the proof went in the paper. So what we do is we show the following equivalence. So you have kind of the space of all multi-fusion, so kind of multi-fusion 2 categories now, but the multi doesn't really matter for the purpose of this talk. So if you take a fusion 2 category C and you equip it with some identification of, so you have kind of this thing which kind of looks at the loops of the center, and then you kind of look at the Muger center of the loops. This is some dominant functor. So you really have kind of a fusion 2 category. You can kind of extract out these 2 pieces of data. This functor is always dominant. So from this piece of data, you always get a functor from rep G to rep H. So, okay, so these are the fusion 2 categories. And then we show, or like, the goal is to show that this is equivalent to the space of, to the following space of commuting squares, right? And sort of, we call these squares the Delphic squares, basically because, they kind of magically encapsulate all the essential data of the fusion 2 category. And kind of, I'll write the Delphic square for you in the fermionic case, which is more complicated than we actually need it. And then I'll kind of unpack what this all means. But you've already seen lots of the data that's going into the square. But doing it this way sort of makes sure that like it's all like coherent, like the classification is all coherent. So here you have kind of the supergroups, H and G, and then a map here is a map rho, which picks a point inside this space. So this BMFC non-degenerate is saying kind of, it's denoting the 2 groupoid of SVEC non-degenerate braided fusion 1 categories. And basically that's just braided fusion 1 categories or multi-fusion 1 categories equipped with an identification of their symmetric center with SVEC. And on the other hand, this WIT SVEC, this denotes the 4 groupoid of SVEC non-degenerate braided multi-fusion 1 categories, and SVEC with equivalences. And so this right vertical functor just kind of, you take one of these braided multi-fusion 1 categories, and you kind of take the WIT class of that, right? And the bottom horizontal functor is just given by, and kind of this bottom horizontal thing is just saying kind of, I have a map from G into this thing, and this is going to be some cohomological data, and this is going to be some action of H on this fusion. So yeah, just the remark is that in the fermionic case, having a square like this really is nice because of these weird extensions that you have to choose. I just want to make another remark, which is that kind of in the fermionic case, there's another slight annoyance, which is that these are all like superspaces actually, right? And kind of, you should think of the superspace as sort of, these are things equipped with an action of kind of the fermion parity, or an action by rotation by 360 degrees. So this is all kind of hidden in the background here. And for the rest of the talk, I just want to basically take this square. So given that you had this equivalence of squares, now, so that's kind of the hard part. And then, once you have this equivalence of squares, then the rest just becomes kind of a parametrization data, right? And so from this square, you could just pick out all the data that parameterizes 2 categories. So I will just, for the rest of the talk, explain to you the parameterization by unpacking the data of the square. And then I'll kind of say a little bit more about how the proof of this equivalence actually works at the very end. So let me do the bosonic case first. So in the bosonic case, they're parameterized by, you have A, a non-degenerate braided fusion 1 category. You have an inclusion of finite groups. You have a map rho, which is basically just an H action on A, which is something we kind of already saw in kind of the physical example. You have a cohomology class, and then you have a homotopy, which is this diagonal map in the square that I drew above between kind of the anomaly of rho and pi restricted onto the subgroup H. And so what do I mean by the anomaly of rho? This anomaly of rho is some sort of obstruction, right? And in particular, it's obstruction to lifting this map from H into Otber into pick of A, right? So it's the obstruction to lifting it to a monoidal 1 functor to pick A. This is sort of an H4 anomaly. And I just want and so this is exactly kind of the anomaly cancellation data that I had mentioned about kind of gauging the H, the diagonal H symmetry in the SymTFT point of view. So it's really nice, and you can see, as promised, kind of if I just had all the knowledge of A and kind of information about the automorphisms of A and its Picard, then the rest is just kind of group theory data. What's also kind of nice is that kind of these three pieces of data I could have just extracted from the Fusion 2 category. But you see, you also needed the last two pieces of data. This kind of actually depends on the center, right? And so, like, you know, you should really think of a Fusion 2 category as a boundary interval type system. So the bosonic case is really quite easy. Let me just fit this into the square, right? So how do you see this? Well, you take a group H, you take a group G. There's a map here, there's a map pi. But now kind of if you break it down, if you break down the square and you kind of unpack what it all means, what you get here is you get odd Burr, and then here you get B of Burr pick of this guy. But this is just the same as K's as this thing, suspended degree 4. So indeed, a map here is just kind of picking out a degree 4. So that's what the square looks like. And kind of, I just wanted to mention a couple of examples, I guess. Right. So you can kind of consider many different situations where, suppose rep H was the Tanakian part of this part, or you could consider kind of if you got the braided fusion 1 category as coming out of condensing some sort of Tanakian part of this guy, then you could get different types of fusion 2 categories. So in particular, you could recover the strongly fusion 2 categories and the connected fusion 2 categories in these types of cases where these things are specific, one categories. So in particular, if H equals G, then you can construct the fusion 2 category, which looks like, well, you take A, you equivariantize by this, and then you suspend. So then you get all the connected ones. And then if H is just a point, so it's the trivial subgroup, then the fusion 2 category you reconstruct is sort of this thing where it's it's kind of this monoidal equivalence. And if A was just vec, then you can reconstruct these group theoretical fusion 2 categories. And the group theoretical fusion 2 categories just looks like kind of, you take something that looks like 2vec G, and it's all the ones that you could get from taking 5 modules with respect to some algebra. So that's quite nice. And now I want to talk about the fermionic classification. So the first thing we want to do is we want to upgrade to supergroups. And so kind of as I said a little bit earlier, if you have a finite supergroup, but earlier I called it GF, but it's fine. You take Z to have order 2, so it's kind of a non-trivial element that squares. Squares to 1. And what I want to do is I want to find, and I want to say that the supergroup lives in an extension of something called the bosonic group in this set 2. And what parameterizes this extension is kappa, right? So that's one ingredient, and then I need to kind of introduce for you the super cohomology coming up. But first, let me give you the parameterizations. So now A is a slightly degenerate braided fusion 1 category. Now I have an inclusion of finite supergroups. I have an action here, which you can think of as kind of a supermonoidal functor of supergroups. So this thing's a supergroup because it's sort of the SVEC linear automorphisms. And then this thing here is some anomaly valued in a torsor over super cohomology. And then of course I need a homotopy between the super anomaly here with this thing. So this is a little bit weird to say, right? Kind of when you say it in these words, like it seems a little bit clunky, right? Like things don't quite work, which is why kind of the commutative diagram actually makes a little bit more sense abstractly. But let me just go into a little bit more of the details of like what I mean by super cohomology and kind of the super anomaly, right? So super cohomology was kind of initially defined with respect to a triplet of data. So you should think of supercohomology as kind of it's a thing which has three non-trivial homotopy groups, namely there's a Z2, a Z2, and a C cross. And the point is that if you have an omega, which is a class inside supercohomology or just a supercohomology cocycle, then you can say that you could break it down into kind of a cocycle that's shifted down by degree 2, another cocycle shifted down by degree 1, and a cocycle gamma. So omega is sort of an alpha, beta, gamma type of thing. So it's like some generalized. So this is exactly some sort of generalized cohomology theory, right? It looks like a truncation of little KO theory. Yeah. So as I said before, if you just wanted to work with classes and you wanted to do computations, then you could go ahead and choose a trivialization for your computations, and this is quite useful in physics. So kind of let me describe what superanomaly for rho is going to be. So what I want to track is basically the composition of the following two maps, right? Like what I want to say is that kind of there's a map rho from here to here. And if you remember from the square, this is like the top part of the square. And then there's like a vertical part of the square that like goes down, right? So I want to go to the right, and then I want to go down. And by going down, you recall that I just take the width classes. And by taking the width class of this thing, well, now this is a braided thing, but this is just a monoidal thing because I took the width class. And by a choice of M&E, I can find some kind of equivalence between this thing and say it's and some equivalence of this with just S vec. And it so happens that kind of this groupoid is just SH suspended up in 4 degrees. And so right. So if you don't make a choice of this M&E, just as a remark, the superanomaly lives in pi 0 of the space of BZ equivariant maps. So really I want to say it's kind of maps from BH into this like fancy group down here, but it has to be kind of equivariant with respect to the action of rotation by 360 degrees. So this is like a little bit more of a complicated thing to unpack. Okay. So I just want to lay out some of the ideas of the proof. And so the idea is that kind of what do we want to do? We wanted to show that fusion 2 categories were equivalent to these commuting squares called Delphic squares. And what you need to do is you really need to build a functor, right, between these two types of things. So building this functor is a little bit difficult. So instead, what we did is we're gonna kind of sidestep the problem a little bit, and we're gonna build a functor to something else. We'll show that the space of fusion 2 categories is equivalent to the following kind of width square. So this is like another commuting square of data. And then what you have is that kind of you have the following thing is that you're going to have fusion 2 categories on the one hand. You have these width squares on the other hand, and then you have kind of the Delphic ones. And the idea is that kind of we showed this is an equivalence here, and then you're also going to show that this is an equivalence here. And so this is the bit here that's a little bit tricky. And so kind of and it requires kind of a de-equivariantization for this to work. But this is the idea, right? Is that to get this equivalence, we show that there's an equivalence here first. So let me unpack the first downward arrow of the equivalence. So this width square is, so kind of roughly speaking, the data of this width square amounts to the following. So you choose a F non-degenerate braided fusion 1 category D. So F, before I just said it was super vector spaces, but to be even more general, right, we could just say it's some sort of super thing if you like. Together with a E width class B, so there's some category B over here, and then you have basically on the bottom arrow. So the bottom map, what is this? This is called a base change, right? It's base changing along the map from E to F. And so this is kind of keeping track of the data, right? Because if F was something that's was something kind of symmetric and E was something symmetric, then a map from E to F is like saying I have a map from like rep G to like rep H, basically. This is encapsulating the data of this dominant functor that I had before. So kind of this equivalently captures this data. And so kind of there's this functor, which we had to work hard to build. So there's this functor called width. And this functor called width is basically a thing that you can apply to Fusion 2 categories, and it really gives you this square back. So now to the last bit to actually do the classification is that you need to have a little bit more knowledge about this functor. And so you need to know that this functor width commutes with limits of finite one. And so what does this mean? It means that kind of if I take what it really boils down to is a statement of equivariantization and de-equivariantization. Basically, if I de-equivariantize, then I'm just then basically these two things are equivalent. So the statement about equivariantization and de-equivariantization is still to be developed. And essentially it boils down to a complete proof that these things commute with limits of finite one. So when I say one groupoids, right, this is really just BG for some groups. So it's really just doing equivariantization. Yeah, so then that finishes the proof. So once you have a working statement of de-equivariantization, you just plug it into this functor of width, and then you get the Delphic squares, and then that completes the proof for you. So yeah, I think that also yeah. So that's all I wanted to say about the talk. So I guess I can end here, and then I'm happy to take questions.
Thank you. Yeah, get started. Can you hear me well? Yeah.
Yes, I can still hear.
I have a very nice question. So can we see the Fusion 2 category as the Fusion 1 category with some extra structure? Right? It's not a good analogy. So.
Right. There's always going to be some. So the idea of this proof is just that there's always going to be. So you can see in the parameterizations, right? Let's just focus on the bosonic parameterization. Is that you see that no matter what, right? Anytime you want to build a Fusion 2 category, there's always going to be a choice of in particular braided Fusion 1 category that I need to like supply the data, right? And so indeed, like your question is just kind of, yeah, you always have to supply kind of this type of data to any Fusion 2 category, which is braided Fusion 1 category data. And the sort of the interesting part of the story that goes back to the very beginning is that the extra things that you were saying is just kind of, all of these mild conditions about kind of the group theory stuff that happens by analyzing the Fusion 2 category, and a little bit about some cohomologies of groups. So this is the extra bit that you were asking.
But can you make a Fusion 2 category from any Fusion 1 category, or you have to select only someone can appear?
Well, I needed to be a braided Fusion 1 category.
Braided. Non-degenerate braided. Okay. And so the other question I have is there some application of the theory of Fusion 2 category to the theory of Fusion 1 category? Can you say something about Fusion 1? Yeah.
So the big application of this was in the paper of Theo Johnson-Fried and David Reuter, where they used basically an understanding of Fusion 2 categories to show that minimal non-degenerate extensions always exist.
Okay.
So this is one of the main applications of Fusion 2 categories. So this really delves into understanding the centers of a couple of specific Fusion 2 categories, among other applications, but this is a big one.
I see. Thank you.
So can I look at the upper right corner of the squares, either the delta or the width square? So this BMFC non-degenerate as well. This is you view it as a group? It's not group, right? I don't know.
It's a groupoid. It's a groupoid. It's a two groupoid.
Okay. So and in the width square, you also view that that part.
Yeah, exactly. So the width square is a three groupoid. It's the three groupoid of width squares.
I see. Okay.
And the three groupoid of multifusion two categories. So we have equivalents of three groupoids.
Okay.
So it's equivalents of spaces.
So will the classification simplify the proof of the non-degenerate minimal non-degenerate extension of Thiel and yeah.
It doesn't simplify the proof because the proof there needs some specific knowledge about two very specific types of non-degenerate braided fusion two categories, actually. Not braided fusion one categories, but they needed specific data of non-degenerate braided fusion two categories.
So my understanding is that.
Yeah, go ahead.
Oh, okay, I see. So my understanding is that there are key part is to prove you have two candidates and one of them is not the center of something, right?
Yeah.
And that amounts to computing some topological environment.
Yeah, there's some anomaly indicator that you have to compute, but that's beyond the classification. That's just something very specific.
I see. Okay, thanks.
Yeah.
So, can you share some comments on so you have mentioned the braided fusion category, right?
Can you repeat the question?
You have mentioned the braided fusion category, right?
Braided fusion two category, you said? Yeah.
Yes. Is there also possible to classify those?
Yes, it's possible to classify those now with this classification, and it boils down to using equivariantization, basically. You can classify them using equivariantization. It's some ongoing work that we have that we're still developing. But yes, the answer is it's possible. It's not very difficult. The difficult part is kind of the formal part of developing a higher equivariantization, de-equivariantization for two categories. But this is formal. This is like a formal thing that should work. So indeed, you can classify it.
So it still contains some finite group data. Or some
Yeah.
I see. Thanks. Oh, one thing that I can think of, so from the SymTFT picture, so you're saying you want to gauge the high diagonal Witten theory to get the boundary condition, but can you get something non-semi-simple on the boundary, even though you have a semi-simple thing in the block?
Yeah, so that's right. So the algebras you have to consider are very nice algebras, like rigid separable algebras. But if the algebra is not separable, then for sure it could be non-semi-simple. But I choose not to do this.
I see. All right.
Like for example, Fibonacci doesn't admit any boundary conditions if you restrict us to the semi-simple world. But Fibonacci actually has non-semi-simple algebras, right? But I don't care about those things.
Okay. Thank you.
Yeah.
So how about the classification of symmetry and attribution to category?
Okay, yeah, that's a bit harder. I don't know. I don't know what to say about selective.
question. Okay. So it seems there is no more questions. So let's thank the speaker again. Okay. Thank you very much.
Yeah, thank you, Sebastian.
Bye. Bye-bye.
Okay, take care.